Now, if instead of bowing, instead of altering the bend, if I keep the bend the same, but bow at different places, you hear I'm getting quite different notes depending on where I bow. And what's happening there is that I'm forcing the saw to vibrate in different modes or patterns of oscillation, as we would call it. And the third big family of musical instruments uses that change of mode in order to change the pitch of the note. And my member of that family is this one, which is 3.5 meters of garden hose pipe. And if I, well, you can see that it isn't a member of the first family because I've only got one. It isn't a member of the second family because I'm not going to bend it or twist it or do anything with it. All I'm going to do is to change the pattern of vibration inside the pipe. And we can get a whole sequence of notes simply by changing the pattern inside the pipe. And of course, as you know, the bugle does it that way. The trumpet and the tubas and so on use a combination of that and change of shape, because the gaps between those notes are fairly considerable and you need to fill them up. So there's the third major family in the orchestra. The percussion, of course, is a very important component, but percussion is very difficult to understand. It's much more complicated than any of the simple melodic instruments, and there just isn't time, there won't be time to deal with all the melodic ones. So I'm afraid percussion has got to take a back seat as far as tonight is concerned. Well now, the next question we might ask is, just what exactly do we mean by this change of mode, change of pattern? And it's important to understand that because it comes in to when we start talking about the quality of musical sound. And to illustrate that, I'm going to use this piece of soft rubber rope, and I have a volunteer already lined up who is going to act as the anchor at this end. And you can imagine, if you like, that this is a large-scale model of a guitar string. And if you pluck the guitar string, that's what happens. You can see, I think, the wave which is travelling up and down, and I think you can feel every time the wave comes back it thumps the bridge. You're the bridge at the moment. And of course each time it thumps the bridge it will move the whole of the sounding board, and so we get a series of pulses at regular intervals. Now that's a fairly complicated motion. A much simpler motion is that. And if you get that frequency in mind, it's the same as the rate at which that wave is travelling up and down. It's what we call the fundamental frequency of the rope. But now if I make the rope vibrate at exactly twice that frequency, then we get quite a different pattern. And I think you can see now that it's a stable pattern. We would call that the second mode of vibration. And you can see that near the middle there's a place where nothing much is happening. We call that, it's one of those corny jokes that physicists sometimes make, we call the point in the middle a node, which is short for node displacement. And you can see that there's nothing much happening there. Now if I go at 3 times the frequency, we get another quite well-defined mode, quite stable, and now there are 2 places where nothing much is happening. And if I go at 4 times the frequency, we get another one. You see, with 3 times it gets more difficult, but I think you can just about see it. I think we'll stop there. Thank you very much. Well, as you can see, roughly speaking, we have modes in the ratio 1, 2, 3, 4, and this is where we have to make one of those dreadful proviso statements. If the anchor at both ends had been much more rigid, and this is no reflection on our friend here, if the string had been more flexible, completely flexible in fact, and so on and so forth, then we would have had a sequence 1, 2, 3, 4, 5, 6 as far as you like. In practice, with real strings, they soon begin to depart from that perfect series, but I don't think that really need concern us too much tonight. And since mathematicians refer to that sort of sequence, 1, 2, 3, 4, 5, as a harmonic sequence, then we tend to call those harmonics. But of course it is important to remember that they're only harmonics if they have that nice, neat frequency ratio, 1, 2, 3, 4, 5. If it goes 1, 2, 3, 3.9, 4.6 and so on, as it sometimes does with real strings, then we can't anymore call them harmonics. We have to call them overtones or partial vibrations. Well, just to complete that picture, let's just have a look on a slide at what those harmonics would sound like if we started with a frequency. The numbers just underneath the notes there are the frequencies, and we go up 55, 110, 165. The numbers on the next row are the harmonic numbers, 1, 2, 3, 4, etc. Right down at the bottom you can see the musical intervals, the octave, the fifth, the fourth, and as we go up the harmonic scale, with the intervals get less and less, and you can see on the stave there we have the corresponding musical notation. And I'm going to play a recording now of exactly what those sound like, starting with the 55, which would be pretty low frequency, pretty low pitch rather, and then we'll go up the scale. That's 55, that's 110, that's 165, 220, we're now 2 octaves above where we started, 275, 330, 385, a rather nasty note, and 440, 3 octaves above where we started, 495, and 550. Those are the first 10 harmonics. And as you can see, they all fit onto the normal musical scale that we're familiar with, except number 7, which doesn't really quite fit. It's a little bit out of tune, and thereby hangs quite a long tail, and I'm not sure that we really thoroughly understand why that is. There are lots of things in this topic that we don't understand, and in a way I think that's one of its fascinations. There are so many things that we don't thoroughly understand. There's plenty of scope for more people to come in and help us to sort it out. Well, the sounds I've been making so far are not really very pleasant. The brass rods and the saw and the hose pipe and even those harmonics, pure tones though they were, are not very pleasant. What is the difference between those sort of sounds and the kind of sound that is made by a good violin or a clarinet and so on and so forth? Well, for a long time it was thought that the principal change was that in a real instrument like a violin or a clarinet, the vibrator is not just vibrating in one mode, it's vibrating in several modes at once. So you're really hearing a kind of chord. And you remember at the beginning when I plucked the string, I said that's rather a complicated oscillation. That could be really regarded as the sum of a whole lot of others. And I just want to demonstrate what happens if we add a series of waves. And if you look at the screen, I think you'll see what happens, and if you listen, you'll hear the change in quality as we add in harmonics. There's the fundamental. Now we add the second harmonic to it, and you can see the change in shape, and I think you can hear the change in quality. Now we're adding the third harmonic, and now the fourth, and the fifth, and the sixth, and the seventh, and the eighth, and now we've got a sort of sawtooth type wave, you see. Now we're taking them away again. And you can hear that we get a kind of wah-wah sound, and in fact I believe that people who play the electric guitar have a thing called a wah-wah pedal, which in fact just increases and decreases the number of harmonics as we were doing there.